Hello everyone. Welcome to the session MLtiverse of Madness. This session offers a practical and intuitive introduction to machine learning, from core theory, mathematics, to working with real datasets, implementation of models through code. We will understand in this session how ML model works, we'll explore it using EDA, exploratory data analysis, and learn how to prepare real world data for modeling. By the end of this session, you will be able to connect concepts with implementation and confidently apply ML in real life while making end-to-end pipeline from raw data to a model evaluation. Moving on. So the question is, why machine learning in the first place? Why did machine learning as a concept was introduced? Well, the answer is quite simple. Um, let's say if you were to find out whether a concert is successful or not, then we can just simply ask a participant of that concert to rate the concert out of a certain scale, like let's say out of 10. And if it's like, let's say greater than 5, we can say that the concert was successful. But now let's consider a scenario where it's far more complicated. The relationships are far more complicated. For example, prediction of house prices. In this, it's not that easy to directly find out whether uh, a price of a house, let's say, cannot be directly found out like that. So, so in this, the relationships are sort of complicated, and this is where we use machine learning. Since we cannot directly define a set of instructions or if else to know to create a program out of it. So we use machine learning, which identifies a complicated pattern, and then uh, we can get the desired output out of it. Okay, moving on.
Uh, so guys, the first core topic for the day is exploratory data analysis. And the core question in hand is, what is exploratory data analysis? So exploratory data analysis is basically systematic process of studying the data and understanding the structure, the quality, and the patterns that are inherently present in the data. Now, these studies help us uncover the distributions, the relationships, the anomalies that are present within the data, and help us model our data in a more efficient manner. Now, a very important question that arises is, how is EDA pertinent to the subject matter in hand, which is, of course, ML? So EDA matters in machine learning a lot because all machine models are trained on data. Data is the backbone of machine models, machine learning models. So if your data does not conform to a certain quality, your machine learning model will also not conform to the quality or to the expectation that you have. And hence, your models will lack. To fix this problem, what we do is that we conform the data to high standards of quality, and hence we ensure that a model makes accurate precisions. Let us understand the EDA workflow. So the first topic that we must understand is, what is the problem statement that we are looking at, and what is the data set that we are looking at. We must first identify the units, the target variables, and how the data was collected to get a deeper insight into what our data is. We must first load and inspect the data and examine the shape and types of data. We'll get into what shape and types are in the session. Then we must clean the data of values that are not required or values that actually cause some trouble in the data or mess the distributions in the data. Then we move on to univariate analysis, which is analyzing a single feature at once. And then we move to bivariate or multivariate analysis, which is analyzing either two, which is bivariate, or multiple features together and how they relate or correlate to each other. Then we move on to statistical and probabilistic checks and to statistical metrics such as mean, mode, median, so on and so forth. And then we move to feature encoding and feature engineering. This is basically scaling the data or scaling or descaling the data, both way it works. and then we visualize to understand the structure of the data and document our findings. After this entire process is completed, we move on to modeling, wherein we feed the data to our ML model. Now let us understand the types of data. There are primarily two types of data on a broader scale. One is qualitative data and the other is quantitative data. Qualitative data, of course, is categorical data, which can be further subdivided into ordinal and nominal. Ordinal data means ordered categorical data, and nominal is unordered categorical data. A good example of ordinal data would be test grade. All test grades are ordered, whereas nominal would be nationality. Nationality, there's no particular order that needs to be followed when mentioning nationalities. Then quantitative data. Now, quantitative data can be continuous and discrete. Continuous data means that the data can be divided into smaller subparts, whereas discrete data means a single instance of data in the set. Now we move on to the basic data metrics. The given data set is a data set that we use as a reference point to understand all the data metrics that we are going to cover. So through this data set, we are going to manipulate this data set and figure out all the data metrics corresponding to this for the better understanding of our viewers, so they can actually go back to this reference set and get an idea of what happened later in the slides. Basic data metrics. First would be central tendencies. Now, there are multiple types of central tendencies. The first tendency that I want to talk about is mean. Now, assume you have a set of values starting from x1 to xn, and these certain set of values are connected by an operator, any mathematical or arithmetic operator. Now, how do you decide that what is the mean? A mean is a value when it is substituted in this set of x values or in this set, the final result does not change. As in, if I substitute x mean to x1, x2, x3 up to xn, the final result of the operation should not change. Now, if the operation is addition, then this mean is called arithmetic mean and is given by the formula summation fi by fi. If the final is multiplicative and not additive, that is, if multiplication is the operation in hand, then we use the geometric mean. And if we are handling ratios wherein division and reciprocals are there in place, then we take the harmonic mean. Then come median and mode. Median is that data that divides your data set into two equal parts. And it is exactly in the middle of the entire data set. And mode is that data that has the highest frequency or the highest number of occurrences in your data set. We've taken small examples from the given data set of 12 entries, the cafe data set that we have. Now, if we want to figure out what was the money, or if we want to project the sales of next 100 customers, we take the arithmetic mean. This is where arithmetic mean comes into place because money is additive in nature. Whereas if you, let's say you define a multiplier, let's say you want to figure out how many people spent more than the base price being set at 250. So if you set the base price at 250 and then you want to figure out the multiplier effect on this, then you have to use geometric mean because all these values are multiplicative in nature and our operator is multiplication. Similarly, if you want to understand some ratio of the data, then you have to use the harmonic mean. Now, moments about the mean. The word moment has a very interesting etymology, if you think about it. If the viewers have come across the concept of moment of inertia, or rather torque, or any of these physical moments, they'd realize that this is the same concept in a different context. Moment of inertia is nothing but the distribution of mass into the distance from the axis from where the force is applied, or from where the rotational force is applied. Torque is similarly force into the hinge position, the distance from the hinge position. So if we were to generalize that concept, any moment would be magnitude into distance from a reference point. And when extrapolated this concept into statistics, we'd figure out that it is nothing but frequency of the observation into the distance from a reference point, usually taken as mean. So zeroth moment of a data means that summation fi into xi minus x bar raised to power 0. So the distance is actually 0, which would give us 1, which signifies the total probability distribution. Now, as we know, the total probability, or the total area under a curve of probability distribution, is supposed to be 1. Hence, the zeroth moment is always equal to 1. When we go to the first moment is basically the average deviation from mean, and it is always 0 when the mean is a true mean. First moment comes into picture when we estimate a mean. Let's say we assume a value of mean and we want to check whether this mean is the true mean or not. Then we put the estimated means value in the first moment's equation. And if we get 0, that means we are dealing with a true mean. And if we don't get a 0, that means that our estimated mean is not the true mean. Moving on to variance, which is the second moment about the mean. Now, variance is basically proportional to the square of deviations from the mean, and it is actually the average of the squared deviations from the mean. So it actually tells us in the dispersion, or rather in the distribution, how much dispersiveness is there, how much dispersion is there, and how much the values vary about the mean. Standard deviation is the square root of variance. And this is particularly important because if you can see from the formulas over here, the unit for variance is actually the square of the unit of x, whereas the standard deviation has the same unit as x. So it is of importance. And another application of standard mean is that it de-amplifies the variance, and hence we actually get to know the magnitude or the comparative measure of mean about the mean, of the dispersion about the mean. Now, this is a plot of the reference data set that we had, the CAFE data set. And as you can see, this green line is the median, the left line is the mode, and the right line is the mean. And we can see the distribution about this mean, how towards the left and how towards the right of the mean, the values behave in this distribution. Now, we have calculated the variance of the samples of outdoor temperature from our reference data set, which was the CAFE data set. And as you can see, in each step, we know the mean was 74.33. So in each step, we have subtracted the observation value from the mean value and squared that distance. And after squaring, we have summed all the differences and then divided by n minus 1 to take the average. Now we use n minus 1 because this is a small data and this is called Bezel's correction. What Bezel's correction is beyond the scope of today's discussion, but viewers are free to look this up online. Now comes the standard deviation, and we have taken the square root of the variance to find out our standard deviation from the data set, which comes out to be 7.67. Now we come to skewness of the data. Skewness is basically the third moment about the mean, and it actually helps us understand how asymmetric the distribution is, as in whether the median is behind the mean or ahead of the mean. As you can see in this picture of distributions, when mean equal to median equal to mode, there is no skewness. When mode is the least and mean is the highest, median in between, it is called positively skewed data because mean is greater than the median. And negatively skewed data is when mode is the greatest and mean is the lowest. The third moment does not give us a comparative measure of skewness. And hence, if we want to compare skewness across different target variables, we must introduce in a coefficient that is called a Pearson's coefficient 1, which is the third moment upon exponent to the power 3 by 2 of the second moment, which is actually nothing but making a unitless entity, because the third moment had the unit cubed and the second moment had the unit squared. So we are actually just eliminating the unit of the data so that it becomes comparable across all data sets. Now comes kurtosis. Kurtosis is basically the fourth central moment about the mean, which tells us how peaked our distribution is, or how flat distributed our area is, also called as tail heaviness. So over here also, the fourth moment gives us kurtosis, which is not comparable in a certain sense, and we introduce a second coefficient of Pearson, the gamma 2, which is equal to mu4 upon mu2 square, which is again doing the job of making this a dimensionless quantity, and hence could be compared across data sets. Now, this is the basic distribution of the cafe data set that we had taken of the variable outdoor temperature. So as you can see, this in this histogram, which is also the distribution is actually signified by this KDE. We shall talk about what KDE is in the future slides. Now we come to covariance. Covariance is basically the joint variability along with the direction of the joint variability of two variables. So basically, we are trying to understand how two variables are moving along with each other. We are trying to understand whether if X increases, what happens to Y. And covariance actually figures out a very linear movement or linear joint movement. It is given by the formula summation xi minus x bar yi minus y bar upon n minus 1. As you can see, this is very similar to the variance formula. And because we are also having a unit squared over here, and variance is also a unit squared. Now, Pearson's correlation, covariance is unit dependent and scale dependent. So covariance is not comparable with other data sets, and we must make it scale independent. To do that, we introduce Pearson's correlation, which is dividing the covariance with the standard deviation of x into standard deviation of y. So because we had the unit of x into y, and standard deviation is of unit x and y, dividing the above units by below units gives us a dimensionless quantity, and it also bounds our values within the range of -1 to 1. Now, Pearson's correlation is a measure of linear relationship, and it is also very sensitive to outliers and nonlinear patterns. So this is the correlation between the spend and wait time, which is a slightly positive correlation that we have with our reference data set. Now we have two other types of correlation, Spearman rank correlation and Kendall's tau correlation. Spearman's rank correlation is used when we want to understand monotonic relationships between the data. We actually understand the rank of each variable compared to the other instead of comparing the values directly. And it becomes more robust to outliers because now you're not taking in the consideration of values that are too distant from the central or majority data, but rather taking the rank of the given observation which itself is a distribution form. Now, Kendall's tau is nothing but pairwise uh, agreement disagreement correlation, which is basically concordant pairs wherein X and Y agree with each other or move together. And discordant pairs are basically when X and Y don't move with each other, so they don't have agreement. This is particularly important for small data sets if we want to find out the correlation in small data sets. We have plotted a correlation. We have plotted a correlation matrix over here of the reference data set that we had. And as you can see there, spend time versus wait time, the Spearman correlation is pretty higher as compared to the Pearson correlation. Spend time versus wait time, the correlation value is 0.94 as against the 0.7 that we got from Pearson correlation. And Kendall's tau is 0.87. So out of all of these, Kendall's tau is the most appropriate for the data set that we were using because it is a very small data set. So 0.87 is the most appropriate correlation between spend and wait time. Now let us understand the concept of quantiles, quartiles, and percentiles. Quantiles are basically equal-sized. Quantiles are basically the boundaries when you divide your data set into equal-sized smaller parts. Let's say you divide your data set into k parts. So each boundary will become a quantile. Percentiles are when you divide your data set into 100 equal parts. Each boundary becomes the nth percentile because percentile is also a special type of quantile. A p percentile signifies that p% values fall behind the p value. Quartiles are also a special type of quantile wherein you divide your data set into 4 equal parts and the boundaries are called q1, q2, and q3, which signify the 25th percentile, the 50th percentile, which is the median, and 75th percentile. It is used to measure the spread or the skewness in the data and also find out the IQR, that is interquartile range, which is q3 minus q1 by 2. Now we get to z-scores. Now imagine your standard deviation being a step. So if you want to find out how far the data points are from the mean, you can find that out in the terms of step, or how many steps away is a certain observation from a central point or central mean. That is called a z-score. And this is also used to find the skewness and the outliers. Now, let us understand what we should do when we encounter missing values in our data set. If we have missing values in our data set, so how do we identify them? We can identify them by counting the null values per feature, the percentage of missing data, row-wise versus column-wise missingness, and virtual checks, which is basically heat maps of how many values are missing. And there are 3 types of missingness majorly. There is missingness completely at random, which is that data's on a there's no pattern between the missing values in the data set. Missing at random is that there is some pattern that can be established, but that pattern is not being able to extrapolate it or generalize to the entire data set. And missing not at random means there is a very certain pattern within the data set from where the value is missing. These 3 are important to analyze why our data is missing and what significance does the missing data have on the entire aspect of the problem statement that we are trying to address. Now we have missing value handling. We can have multiple ways in which we handle missing values. First is deletion methods. We delete missing values basically in list-wise deletion when we remove the entire rows wherever a certain feature has a missing value. This can only be done when there are very less number of missing values, or else there would be a lot of missing data, or you'll lose a lot of data from your data set. Then there comes pairwise deletion, which we use with, it is basically not a deletion in strict sense, but rather a fact that every statistics is computed without the values that are missing. So there becomes a lot of inconsistency amongst the data. Missing indicator methods. If the missing values are extremely important, we can add a binary bit or a binary flag that indicates the value is missing. Then we have imputation methods. We can actually replace the missing data with mean, mode, or median. We use mean when the data is normally distributed. We use mode when the data set is small, and we use median imputation when there's a skewed data distribution. There are also conditional imputations wherein there you can devise an algorithm for imputing, wherein there is a decision tree and a lot of decisions of yes and no happen to decide what value is the missing value going to be imputed with. Now, outlier detection and handling. Uh, what is an outlier? Outlier is basically a value that is very distant or that significantly deviates from majority of the data. So there can be point outliers, contextual outliers, collective outliers, and we detect outliers in EDA by either by box plots, by skewedness, or by statistical methods such as IQR method, wherein we check the values that are outside the Q1 minus 1.5 of the IQR or Q3 plus 1.5 of the IQR. Or we can also use Z-score. If the Z-score of a point is more than 3, we consider it as an outlier. Now, outlier detection and handling. We remove an outlier if the value is absolutely absurd. Only then we remove an outlier, or else we stand a chance to lose the data that is important to us. There's one more method called capping or Winsorization, where you cap at certain fixed percentiles. Let's say I will cap my outliers on first and 90th percentile. That would mean that all values that were beyond my 90th percentile would be brought back to 90th, and all values that were below my first percentile will also be imputed with the first percentile value. If our data set is very skewed and there is a lot of outliers in our data, we can also perform transformations on the data set to make them not skewed or to reduce the impact of skewness. One such transformation is log transformation, which is basically that we put in the log value of each observation instead of the absolute value itself. This brings the data and conforms the data to a normal distribution. A more complex and sophisticated form of transformation is Box-Cox transformation, which is a parametric transformation wherein the parameter lambda can take in any value between -1 and 1, and each value signifies something. For example, the -1 signifies an inverse transformation, the 0 signifies a log transformation, the 0.5 signifies a root transformation, and 1 signifies no transformation. Now we come to visualization of data. Basically, we need to visualize the data to understand the patterns and structure of the data. A scatter plot is a plot that shows individual points on our data, and a line plot is a plot which connects these certain individual points by straight lines and is used to understand the patterns or trends in the data. Other visualizations are bar plots, which are basically categorical data representations against their aggregate statistics, and histograms, which is basically continuous numerical data distributions grouped together by intervals called bins. They are basically used to analyze the distribution and skewness of the data. Then we have box plot. So a box plot is a special type of plot wherein the box actually is the IQR range, Q1 to Q3, and the tails of the box plot are 1.5 into the Q1 minus 1.5 of the IQR and Q3 plus 1.5 of the IQR, which actually gives us the whole box plot, or basically the whole distribution insight. And the values that are outside of the box plot are called whiskers, and these are basically the outlier values. Now let us understand EDA with the help of a notebook, wherein we take the Titanic data set and try to analyze the code. Basically, if you look at this EDA, the first step that we do is we import the libraries that are important for our EDA. NumPy, Pandas, Matplotlib, and Seaborn are few of the most popular libraries for EDA. We load the data set, and we load the data set into a data frame, which is D1, which is available in the Pandas library. We print the head of the dataset, that is the first 5 rows of the dataset, to get a understanding of what the dataset looks like and what are the different features within the dataset. We can print the shape of the dataset, which is the number of rows and number of columns, or we can print the info, d1.info, which gives the information about the dataset, like this, which tells us the different parameters, the different features, the different non-null values in our dataset, and the different data types of a dataset. Then the first thing that we have to do is identify the number of null values in our dataset. So as you can see over here, there are a lot of null values in the Kbin feature. So Kbin feature has 687 null values out of 889 values total. So this means that there are a lot of null values in the Kbin feature, and hence we cannot really make any useful or meaningful assumption out of the Kbin feature. This is basically the percentage null values of each feature. We can also describe the dataset, which describe function basically gives us all the basic data metrics of the dataset. So the count, mean, standard deviation, minimum, maximum, 25th, 50, and 75th percentiles of each feature. Then we come to the visualizations to understand the structure of our dataset. So basically here we have plotted a bar plot, or rather a count plot, which counts the frequency of people who survived and did not survive in this Titanic dataset. And this is the same distribution in a pie plot form. Then we use a histogram representation of our age feature. And the blue line which you see over here is actually KDE, which is kernel density estimation. This basically smoothens out the distribution function for us. So this line actually represents the probability density function over here. Then we have a box plot distribution. The box plot distribution actually maps out the number of outliers in the fair feature and how these outliers are present on the right side. So this makes a right skewed data. We can also see the median line over here. The line that runs through the IQR in the box plot is the median line, or the 50th percentile line. Now we have count plot for male and female, number of passengers. And these are the relationships that we must understand before feeding the data into a model to make meaningful assumptions and to derive meaningful outcomes out of our model. This is basically the survived versus class. So this is passenger class 1, 2, and 3, and the percentage of people who survived in these classes. Then we have a box plot, which will tell us the number of outliers in the survived and non-survived data, segregated by their ages. Now we have a correlation heat map to figure out which quantities are highly correlated. So as we can see, the P class is highly correlated. The P class is highly correlated with the age, and the survived class is highly correlated with the sex. So these are the metrics that tells us how dependent or independent each feature within the dataset are. Now we come to missing value handling. So as we saw that there were a lot of missing values in the K-bin. So as you can see, in K-bin you have 65 to 68% people missing who did not survive, and about 30% missing data in the K-bin feature of the people who did survive. Now we apply the median imputation method, wherein we fill the missing data with median values. The median imputation gives us a distribution as such. The red one is the original one, and the green one is the filled one. As you can see, the distribution is not preserved when we do median imputation because K-bin class had a lot of missing values. So in such a case, we must preserve the distribution, and hence we preserve a distribution in the next plot. This is a uh, distribution preserved imputation, wherein we have randomly chosen values throughout the distribution so that we maintain the overall nature of our distribution to impute the missing values in the data. Now we have outlier handling. So as you saw, the fair data is very skewed. In the above box plot, it was very right skewed. There were a lot of values that were outside of the interquartile range and outside of the box plot as well. So to handle this, we can perform a log transformation. And this is particularly helpful when we are dealing with models such as linear regression models, which assume normal distribution of our data. So this is after we perform the log transformation. This is the histogram and the distribution plot after we have performed the log transformation of the data. Now Arav shall explain the ML models.
Thanks, Ashutosh. I will now take on from here. Shrish, could you share your screen? Yeah. All right, guys. So I'll be taking on from now. I'll be starting with the types of machine learning models. So based on training supervisions, there is a supervised learning model. Here, basically, it's trained using labeled data and it's used for prediction. Examples are linear regression, logistic regression, etc. Then is unsupervised learning. Here, there are no labeled outputs. It finds hidden patterns. Examples can be k-mean, hierarchical clustering, etc. Next is self-supervised learning. Here, followed by semi-supervised learning, which is a mixture of supervised and unsupervised, and then comes reinforcement learning, which learns through rewards and penalties. It's used in robotics and gaming. Further, we can classify as whether or not they can learn incrementally. So it comes like batch learning, which is also called as offline learning, or second is online learning. And on the third basis is whether they work or not. So instance-based learning or model-based learning. Next up, I'm going to talk about Shrish. Could you go to the next slide? Next, I'm going to talk about feature engineering. So, what is feature engineering, right? Feature engineering is basically the process of transforming raw data into meaningful input variables. And why it is needed is simply because better features will give you better accuracy, will reduce the noise, allow the algorithm to capture real relationship instead of just guessing from messy data and from the noise. So next, I'm going to talk about the different processes of feature engineering, right? So there are the steps are feature selection and feature extraction. So what is feature selection? Feature selection is the process of choosing the most relevant variables from a data set So the model will become faster, will act faster, is more simpler, and is just more accurate, right? Feature selection has three methods: filter methods, wrapper methods, and embedded methods. So filter methods basically select features based on statistical tests, right? And whereas wrapper methods, they try different feature combinations and evaluate using a model. And embedded methods, feature select happens during model training itself. So now the examples are on are correlation, chi-square test, mutual information for filter methods. Forward selection is for right. Now I'm going to be talking about feature extraction. So feature extraction is a process of creating new features from raw data by transforming it into a lower dimensional, more informative format, right? Now, these are the types. PCA, principal component analysis, keeps maximum variance. Then there is linear discriminant analysis, often used in classification problems. Autoencoders, neural networks that compress data into a smaller representation, are autoencoders. And then text feature extraction like bag of words, TF-IDF conversion, etc. Next, I'm going to be talking about the confusion matrix, right? This is a evaluation matrix for classification models, and it is very important, right? So this graph is the only thing you need. So as you can see, there is an actual class and a predicted class. Actual class is the actual case, actual scenario, whereas uh, the predicted is done by the model. So if the actual class is same as the predicted, if the actual class is same as the predicted class, then it's true positive. If the actual class is if the actual class is predicted to be true, whereas the predicted is false, then it's false negative, right? Similarly, if the actual class is said to be negative but it's predicted to be positive, then it's false positive. And if the actual class is said to be negative but predicted negative as well, then it's true negative. The table is a very accurate description of how you could even learn. So for precision, you could see it's right below true positive upon true positive plus false positive. Similarly, sensitivity is also known as recall, and you could learn it as which is in the horizontal line of the true positive upon true positive plus false negative. Similarly, you could learn for specificity, accuracy, and negative predictive value. Next, I'm going to be talking about the evaluation matrix for regression models, right? So, the best way I could tell you guys about this is by an example. So, a training data set is used to predict item sales where two items, I6 and I7, have been given, right? Whose actual values is 80 and 75, but the predicted is 75 and 85. So now the first one is mean absolute error. Now, how does somebody calculate mean absolute error? Shrish? Next slide. Yep. So now, as you can see, the mean absolute error can be calculated in the follow as written in the following formula: 1 upon n summation of yi minus yi cap. Now, this is basically yi is the actual values, whereas yi cap is the predicted values, and we have to do the summation of all the values. So 1 by 2 into mod of 80 minus 75 plus 75 minus 85. When you calculate it, comes off as to be 7.5. Now the next model will be mean squared error. Here it's the same formula, just the mod will be squared. So if you remember the previous slide, it was 15. So 15 square would be 125. So we get 125 by 2, which is equal to 62.5. The next model would be the would be the coefficient of variance, which is basically root mean squared error upon the mean of yi say, which is here. So yi here is L1, L2, L3, L4, and L5, right? And so we add all of those, divide by the total number, which is 5, and which is 500 by 5, so we get 100. So the root of 62.5 divided by 100, we get a covariance of 0.08, right? Now I'll be talking about the bias variance trade-off. This is very important, right, in terms of classification and this relation. So very simply saying, if the model has a very high bias, it basically means is underfitting. Now what does underfitting mean? Basically means that the model is not at all flexible, right? It's simple but it's not at all flexible, and it makes strong assumptions. And in this model, even if you change the value by a little, it wouldn't really change the graph, right? Now in overfitting, the model has very high variance. That means it's very adaptive in nature. It can adapt to almost any change done in the model in the data set, right? And it's super complex. As you can see, it connects to all the data points, and it's super flexible. But in these two cases, what do you guys think? Which one is the better model? The answer to that question is that none of this is the ideal model or the ideal case. The ideal case would be a low bias and low variance case, which has a good balance, and which has a limited degree of freedom, not too rigid, not too flexible. So this is the bias variance trade-off. Next, I'm going to be talking about the linear regression model. Now I'm going to be talking about the classification model. So linear regression is a very important and is a very important model in machine learning. So exactly, so I'm going to be explaining it to you via a example. So house prices tend to increase with size, but the scattered data makes accurate estimation difficult. So linear regression will solve this problem by fitting a best fit line to the data, which allows us to predict the house prices, right? So now the next slide would be about how the linear regression works and what is the linear regression equation. The linear regression equation is f of x equal to wx plus b, where w is the weight, b is the bias or the intercept. Now, another thing that you need to know while knowing linear regression equation is the cost function, right? Guys, 1 second, I need to give my attendance. I'll continue. Cost function equation. So the cost function calculates the average squared error between predicted and the actual values, right? We adjust w and b to minimize the cost function, which gives us the best fit line for the data set. I'll be back giving it. Okay, I'm back. So the next slide would be the gradient descent. So in linear regression, many lines can fit the data, right? But the problem is that the challenge is finding the one with the least prediction error. So the solution to this is the gradient descent. Gradient descent systematically adjusts the slopes and intercepts to minimize the cost function and identify the best fit, right? So gradient descent algorithm, so it is done till the time the model gives almost negligible changes in w and b, right, in the weight. So as you can see, the formula: w stands for weight, b is the bias, alpha is the learning rate. Now learning rate should neither be too big nor be too small. It should uh, it should be the right it should be set in the right way. M is the total number of training examples, and X is the input value, and Y is the actual output value. Now I'm going to be talking about basically gradient descent minimizes the cost function by moving in the steepest downward direction, helping linear regression find optimal values of W and B for the best fit. So this is a graph. As you could see, if you move a little, you could find the most local minima. Next is logistic regression. This is another very important ML model right? This is basically the output is binary, like, right? So it'll be either a yes or no situation, and it is very useful in terms of scenarios where you want to like check whether the answer is correct or not, or uh whether a patient has a malignant tumor or not, right? So I've taken the same example, and this is the sigmoid function, which will be in the next slide, which I'm going to be talking about. So the next I'm going to be talking about is the logistic regression equation, which is g of z is equal to 1 upon 1 plus e raised to minus z, right? And g of z is so it stands between 0 to 1 value, like I said, right? This function is called the sigmoid function. It converts any value into a probability between 0 and 1. And this is the equation that I was talking about, right? And now I'm going to be talking about the decision tree, right? So now decision trees are non-linear models that recursively split the dataset into smaller subsets, like Ashutosh had mentioned, forming a binary tree until leaf nodes become pure or contain predominantly one class. So now in this example, or in this photo that I've taken, is that the data sets contain two classes, right? Red and green. Okay. And that there's x0, which is the horizontal axis, x1 is the vertical axis. The problem is that if you see, the data is not linearly separable. It's made in a way that a single line cannot separate the classes if you could see the green and the red dots. So now what do we do? So in the next slide, I'm going to be talking about how the tree splits the data, right? So the first split is done at x naught lesser than 12. The second split is done at x naught lesser than 9, and the third split is done at x1 lesser than 9. So basically, you classify a new point by following decision rules from the root node, which is x naught lesser than equal to minus 12, to the leaf node, which is x naught lesser than x naught lesser than equal to 9, and x1 lesser than equal to 9. So here, moving left would be a yes case, where you would get the same set of red dots, whereas moving right would be a no scenario, where you would get a mixture of data set, or an impure uh, data set, right? So now the next slide, I will be talking about the next slide. Yep. The next slide is how the prediction works. So some leaf nodes may contain both classes, right? Like I was talking, like some cases you might get both classes, like the red dots and the green dots. And what are you going to do? In such cases, the model assigns the class with the highest number of data points. And this method is called majority
Okay, I think Arav is facing net issue, so he'll be joining back in just 30 seconds.
Uh, am I audible, Shrish?
Yeah, you're audible.
Okay, guys, I'm so sorry my internet had gone. But I'll be moving to the next model. I think I've explained majority voting. Um, the next I'm going to be talking about is the how do we measure the impurity. So measuring the impurity would be done by a concept called entropy. Entropy measures how mixed the classes are in a node, right? I was talking about how the classes are mixed, and now entropy is going to tell me how much the classes are mixed in a node. Now if entropy is now this is the formula of entropy. Okay, is it the summation, is the minus of summation of from 1 to n, right? Pi of log base 2 pi. Now here pi is the probability of the class, right? Summation is the sum of all classes, and the negative sign is very important. It basically ensures that entropy is always positive, right? So now if entropy is equal to 0, the node is completely pure, right? It's a single class. If it has high entropy, let's say it's close to 1, or it's almost 1, or if it's 1, node is highly mixed. And if entropy measures the disorder in the data, right? So a pure node contains data from only one class, and an impure node contains a mixture of different classes, right? Now the next slide I'm going to be talking about is how do we choose the split that best separates the data, right? Now, information gain helps by selecting the split that maximizes the reduction in entropy. So, the information gain is the E of parent, which is the entropy before the split, and summation minus summation of the weight of every child into the entropy of each child node, right? So the W of I is equal to samples in the child upon total samples, right? And we have to take a summation of that. The basic interpretation is simple. If it has high information gain, the split greatly reduces impurity. Low uh, information gain will little reduction in impurity. Now the next slide is, so when should we stop the tree from growing, right? So the trees can grow very deep and memorize training data, and this will cause an overfitting problem, which I talked about. So to prevent this, we use stopping criteria such as maximum depth, minimum samples per node, and minimum information gain. Next, I'm going to be talking about perceptrons. So the next slide, I'm going to be talking about perceptron. Shrish, could you? So the decision tree, so the perceptron model is basically, uh, I'm going to be talking about the perceptron model, and it will be having weight, and it'll be having one bias, and it'll be having several inputs. So that is also a classification model. There are two types of these, which are, one will be a simple perceptron model, and one will be a multi-layer perceptron model, which will have a starting layer, which will have some hidden layers, can have any number of hidden layers, but at the end will have only one output layer, right? So now, uh, the perceptron model, uh, so as you can see in the diagram, like I was mentioning, there are several inputs like x1, x2, x3 with different weights, w1, w2, w3, a bias, which will be which will give us one output, right? Now the f is equal to, now if wx plus b is less than equal to 0, it will be the function will give 0. But if it's greater than 0, then it will give 1, right? Here w is weights, b is bias, like I have mentioned. Going to the next slide, I'm going to be talking about the activation function, which is basically also like called the step function, as mentioned in the graph. As you could see, it has a step structure to it, and converts the weighted sum into a binary output, 0 or 1. And as I was mentioning, if it's z is greater than equal to 0, output is 1. If z is less than 0, output is 0. The perceptron also updates weights when predictions are wrong, right, and helps the model learn from error. So that is the formula. And now I'm going to be talking about, in the next slide, I'm going to be talking about the multi-layer perceptron, like I was saying. So like I had mentioned, input layer, which has these x1, x2, x3 till xn, there'll be hidden layers involved, and but there'll be only one output layer, as you could see, right? The data flows from the input layer through hidden layers where features are learned, and finally reaches the output layers. So why MLPs are like a very important thing is because MLPs overcome the limitation of single perceptrons by modeling nonlinear decision boundaries, right? So in the next slide, I'm going to be talking about the okay. Now I'm going to be talking about how multi-layer perceptrons work. These work in basically like two things that you must know are forward propagation and backward propagation. Forward propagation is basically data moves from the input, goes through hidden layers, goes to the output layer. Simple. And back propagation is it measures the error between actual and predicted output. So it propagates the error backward through the network, hence the name backward propagation, right? And it updates weights to reduce the loss. So this is the loss function formula, the weight update formula, right? I'm going to be going to the next slide, which is, and I'm handing over it to Shrish now. We will be starting with the ML code analysis.
Okay. So yeah, you guys can see my screen, right?
Yep.
Okay, so let's begin with the fun part. These are all the libraries which you would require over here. And let's quickly run this up. Okay, so over here, this is installing all the libraries, and over here we're importing all the libraries which are required. We're going to use primarily sklearn, and this code is going to give you a small demonstration of primarily only logistic regression model. Um, we're going to use Titanic dataset, which is a very common dataset you can easily find on Kaggle, and also we're going to use Seaborn to load the Titanic dataset. df.head. Okay, what df.head does is it gives you a basically 5-row idea of what the dataset looks like. .info gives you a general information of all the data in the dataset. Like over here in the column, we can see that survived is basically consisting of integer values. Then we have object values and categories, etc. So yeah, let's have a quick look at our dataset, but in a more formatted way. So over here, you can see basically all the rows are representing one individual and all the columns are features which we're going to consider for making the prediction whether the person is alive or not. So over here, okay, let me just quickly walk you through all the features once. I don't think I have to explain the survive feature. PC class is mainly, it's encoded. So encoding is something which was covered by Ashutosh. Basically, we have one for like upper classes and three for lower classes. Then we have SIBSP, which is basically saying that is there any siblings of this individual on the board. Similarly, parts is for parent or children. Fare is how much the person had paid for their tickets. Embarked is basically the port on which they deported the Titanic boat. uh, this is a repetition, that's why we haven't considered it later. So class and PC class are pretty much the same thing. Who is again not required. Similarly, this is not required. This has a lot of null values, and we're not going to consider these ones as well. So out of all this, we are only taking the important values or the relevant values, which is this. Okay, so after selection, we can see this is the final data set which we're going to use. So now we're going to basically split this data set into two parts, X and Y. Y is our targeted column and X is all the other individual column which we are going to use to predict the targeted column. And I have used dot drop. What dot drop does is basically it's going to drop a certain column. So I'm going to drop survive column and I'm going to put everything else other than that in X and let Y be the survived column. Okay, then we have train test split. What train test split basically does is it splits your data set. So like right now I have a data set in X and Y. Now I'm going to make two further splits in X train and X test, Y train and Y test. And I'm going to use the train part for the training part and testing for the evaluation part. Test size 0.2 is just here to signify that 20% of the data is the testing one and 80% is for the training one. Random state equal to 6, 7 is basically it's basically telling that if anyone else were to use the same data and if they were have entered the same value, they would have got the same set of rows in each and every train and test divisions. And we are also splitting this early. That's mainly to avoid data leakage. That's a rookie mistake which most of the people make while coding. So the question is, what is exactly data leakage? Data leakage is basically when your model somehow indirectly sees the or sees certain qualities of your testing data. So now basically it's as if you were to give an exam, but you have already seen the glimpse of the question paper. So you're already cheating, something like that. Okay. Once we're done with this, let's quickly look at the head of X train and X test. Oh yeah, one more thing. In this, it's in a ascending order, and since the splits are random, so over here the index value or the order has been completely ruptured. Okay, now let's see if there are actually any null values or not, because we have to first handle the NaN values as mentioned by Ashutosh before. NaN, you don't need these values because they throw up an error basically, and they do not represent anything. So yeah, let's see this. DF is the main data frame, which is the one I've used for to initiate the entire data. Dot is null is a predefined function which tells us does it have a null value or not, and dot sum is basically summing the entire things on the rows. I have basically applied a small mask, and through this I can see that age has 177 null values and embarked has 2 null values. So let's quickly drop this. Okay, yeah, one more thing. This gives a small warning. That's because I've used in place equal to true while I'm modifying the data. In place equal to true, basically what it does is it will replace your entire data set with the data set which you have modified. But in this, just to keep everything in one line, I modified at the same time made a permanent replacement. That's why it's giving me a warning, which you can easily cover up by using a reassignment, which I've done over here. Okay, so now let's see quickly again X-train and X-test. Okay, right. As you can see, the null values are gone, which were before visible. Now we're going to do the same thing, but for categorical values. So in category, rather than in age, where we specifically used basically mean values to fill the data set, over here, we're going to use mode. One more thing which I forgot to mention was this that in this for testing as well, I have used training dataset mean. This is again in order to avoid data leakage because you do not want the model to see the testing part. Okay, yeah, coming back. The same warning, which again is going to be covered by reassignment. Over here, I've used mode, like I said. So the embark which has been replaced, or sorry, the embark which has appeared the most amount of time is going to replace the none values. Let's move on to feature engineering. So in this, I have created a new column with the name of family size. And what basically I'm doing is, since I told you SIBSP is all the siblings, so family size is all the siblings of that individual plus any parent or child plus one is counting that individual themselves. Then I have introduced another column, fair per person, in which I'm just dividing fair by the entire family size. Just to show you a quick representation of how feature engineering is done. Okay, then we have age group. another column which I've made. Now in this I've used dot cut. Basically, if I were to like quickly shorten this out, I am making, this is a discrete data set, right? As you can see on top, it's completely discrete. What I'm doing is over here, I have defined certain bins values like 0 to 12, 12 to 20, 20 to 40, and so on, a continuous data. And I have basically labeled all of these one continuity and like child for this teen, adult, etc., etc. Trying to just classify the ages into different groups. Okay, and this is similarly for X testing. Now, since I have already considered SIBSP and Parch in the previous feature engineering column, so I'm going to again just quickly drop them off. Okay, now let's see a quick draw box plot of fair. So of in this fair, we can see these are the outliers. Now here is another mistake which most of the rookie developers might do. Since they saw an outlier, they just straightforward jump on and handle them. So technically speaking, outlier is a value which is too off from the majority of the values, right? But at the same time, if I were to, let's say, take values from a sensor reading, and then from that sensor reading there are certain off values, then it makes sense that I can just cap them or remove them. But in these outlier values, they have a essence, they have a information inside of them. Like most of the people would be middle class people. Uh, so that's why all these fair are basically representing the upper class people, those who actually have paid a higher amount in their ticket to get certain luxury privileges. And this can actually tell whether the person survived or not, because they might evacuate off the richer ones first. So that's why rather than directly removing or capping them, we're going to use log transformation over here. So before I use that, I'll just quickly show you the hist plot of this as well, where we can see how much skewed this data is. Now, what log transformation, as again mentioned by Ashutosh before, what it basically does is, uh, it's like somewhat like scaling. Now, I'll explain you what scaling is a bit further, but basically speaking, all the values which are at the very extreme edge, it's going to space them a bit more, and those who are already in the average is going to get spaced less. So at the end, it's going to again be uniform. And after applying the log transformation over here by using np.log1, you can see how much it changed, right? From this completely on one side to making it a bit of more uniform. Okay, now let's just quickly replot the box plot to see that it actually made a change. And yeah, voila, we can see that. We can see that now the outliers are far more less than which were over here. And we haven't technically touched the outliers. I did not cap them. I did not remove them. It's just that I introduced some spacing in between, due to which now the outliers are far more less than they were before because of the way outliers work, right? Above 75%. Okay. Now this column I'm just sorry, in this cell I'm just simply replacing the original. Okay, now as we know that we have categorical values in our data set, basically strings like we had women and men or embarked, etc. Now our model cannot directly understand string values, so we have to use some sort of encoding so that our model understands what's going on. And for that, I have used get dummies. Now there are, again, as mentioned before, there are three ways. We have we have basically one hot encoding, we have dot get dummies, and we have ordinal encoding. So over here I've used get dummies to explain you later, which you'll see later why I've specifically used get dummies. Okay, now after applying get dummies, and yeah, one more thing, drop underscore first. Well, this thing, it's basically like removing one of the values. What get dummies does is, wherever that category, that specific string appeared in that column, it's going to take that out and make it into a new column. And now wherever that string appeared, it's going to be marked as 1, and wherever it did not appear, it's going to be marked as 0. So let's say if a column has like what, 5 unique values, it's going to make 5 new different columns from that column, which are going to represent one unique values each. Now, the downside of using .get dummies is that it basically just makes your data set too huge. Just imagine if I were to have something like nationality, which has like 100 different nations, right? If I use get dummies on that, I'm just making that one column into 100 new. And if I were to predict something which already has a lot of features, my data set is cooked. So yeah, after applying .get dummies, this drop first is basically going to just reduce that last column so that whenever the model sees everything is zero, it's obvious that the other part which has been dropped has to be one. Yeah, let's quickly see our data set. So yeah, like I said, drop dependency has been removed in age groups and so on, so on. Okay, now this was the reason why I have primarily used .get dummies. What exactly is happening is over here, since I told you before that train test split just makes randomly splits, right? So just imagine once that we know basically that z equals to w x plus b, right? Where w are the weight. Now let's say through training our model learned certain values of w. Like let's specifically consider for just embarked. So let's say it learned w1 times embark of q plus w2 times embark of s plus w3 times embark of c. Let's say like that. Now, what are the odds of this? Actually, it's quite slim, but there's a possibility that in testing data set, there was no certain row which had s. Okay, let's say c. There was no certain row which had c inside of it. So in testing data set, there is no C. And now if I were to use get dummies, only Q and S would be the two different columns which were made. And from that, if I were to use drop first, only one of them would be there, right? So in testing data set, when this equation would be applied, the model would be confused that what am I supposed to multiply W3 with? Because W3 was assigned for the embarked equal to C, but there is no C in this particular row. And this will throw off an error. Probably the model will yell at us. And so basically, in order to not use this, you can use directly one hot encoding, and there is a parameter unknown equal to ignored, which handles this, or will use the manual way to handle this, where basically I have used dot align. Now, what exactly dot align does? It's a concept of basically taking the values, the column headings of training, and then matching it with testing. Now, let's say if the test did not had a certain column, it's going to be applied, or it's going to be simply padded with zero. So yeah, I'm going to align test and join equal to left. This means basically I'm joining it with the training data set, access equal to 1, and fill value, like I said, is going to be 0. Now, access equal to 1, if I were to help you guys visualize it, imagine you have a cursor, or like let's say you have a mouse. Okay, since you guys can see my screen, I'll just use my mouse to display it. When you have access equal to 0, you go row wise like this. And when you have access equal to 1, you go column wise. So if you were to, like, let's say make an alignment, you'll align them using the columns. So that's why we have access equal to 1. Otherwise, in normal way, if we were to iterate it like this, it's 0. Okay, now let's use scaling. Now, why do we exactly need scaling? Okay, firstly, consider this as a thumb rule. In any model where gradient descent is used or distance is taken into consideration, for example, let's say KNN, if you were to consider KNN where you use distance, any outlier is going to drastically affect something. Not just that, but in gradient descent, where let's say we haven't used scaling, the descent would be quite zigzaggy. It's not going to be smooth. And that's mainly because we haven't used scaling. So let's say, okay, you know what? I'll give you a practical example of this data set itself. Okay, let's say we have things like fair, and let's say we have age. So in this, I can see the fair is 9 and the age is 47. Or if I were to consider, okay, let's go with this example itself. It's fine. Or let's say age and fair per person. Now it's 47, and here the magnitude is 9. Now, this entire model just understand mathematics. And mathematically speaking, if you were to multiply something by 47 and 9, the product magnitude with which you have multiplied by 47 would be obviously more than multiplying by 9. Yeah, that's basic math. So the thing is, now model might misunderstand it. It might think that age is more valuable than fair or fair per person, just because the age is 47 and the fair magnitude is less. But in reality, it might be the opposite, that riches are getting first priority. So if a person has higher fare, if the person has paid higher fare, this means that person is of a richer class and they might be evacuated first from the Titanic ship. So it might be completely the other way around. But because of this magnitude difference, model might uh, perceive it in an incorrect way. So we are going to use scaling. What scaling does is, now it's going to scale these magnitudes such that their essence is still captured, but the magnitude is handled. Now, again, notice very carefully, why have I used dot fit underscore transform in train and testing just transform? Well, it's the same reason, data leakage. Fit underscore transform, it's going to learn, or it's going to like basically make those scalings, and on the basis of those data set, it's going to just directly apply it on the on the testing one. Okay, now let's quickly train the model. Over here, I've used max underscore iter equal to 500. Now, this is a concept of gradient descent. Basically, max underscore iter tells you that the entire descent is supposed to happen in at max 500 attempts. Usually, or technically speaking, I keep this on 200, but just to be safe, I've kept this a bit extra. And other than, yeah, the syntax is quite simple. Model.fit is supposed to fit the entire model on two data set, xtrain and ytrain. Sorry, xtrain scaled. My bad. I changed the data set in between. Okay, and also for boosting of performance later on, I want you guys to explore this yourself. You can use hyperparameter tuning, because in this there's just one parameter which I've used. Technically speaking, uh, hello. Hello, am I audible?
Yeah, you're audible.
Yeah, sorry, my mic actually got disconnected. Technically speaking, you can use many other parameters as well, and that's something beyond this lecture. I'll cover it some other day. Okay, then let's move on to the next cell. In this, I've basically defined a variable with the name of importance, and what I've done is I've used model.coefficient, or the weight of this model. That into a series full of data set. That's why I've used pandas.series. And in index, I'm using the training column. So whatever name of the column were used, they're going to be displayed on left, and the coefficients are going to be on the right side. And from that, I've extracted the top feature. This means these were the feature which had the maximum amount of weight. Okay, wait. If I were to, this might be better. Okay, now you guys can visualize it. So after this training, these were all the weight which our model learned for each and every parameter. Now, whenever the testing data is going to be fit, it's going to first go through the pipeline, and then it's going to land up over here. This entire thing, each and every parameter of the testing data set, is going to be multiplied by all these weights. And through that, after passing it to the entire function, we're going to get the final output, which we're going to use these, which we can manually see that the maximum impacted feature was the gender of that person, which has the maximum magnitude. Okay, now let's move on to making the predictions. Okay, so the syntax is again quite simple. Just model.predict. Predict on what? On on X test scale data set. That's it. And now our model has made predictions. We're gonna also use predict proba, which basically tells you the, see, what happens is in dot predict, after making the prediction, the threshold value is 0.5. dot predict proba, what it tells us is it tells us the entire probability for each and every different column. So like in linear regression, we are predicting numbers, and then in logistic regression, using the sigmoid, we're just converting it into ones and zeros, into a label, into a binary label, right? So this returns us all the magnitude of the probabilities. um okay, maybe I used the uh okay, maybe I used the inbuilt function incorrectly. I have to go through the document of this. Okay, for the timing, I'll just keep this on hold. Let's go to the next part, which is the evaluation. These are the modules which we're going to use for the evaluation part. And yeah, right. As you can see, we have accuracy, precision, recall, and F1 score. What basically accuracy tells you actually highly misleading. It's misleading in the sense it tells us it is imbalance, which in practical scenario, most of the time it's gonna be highly imbalanced. Uh, so let's say your model did not learn anything and your data set is highly imbalanced. There are two classes, 0 and 1, but most of the time your class is just 0. Now, the problem with this is that your model did not learn anything. It's going to just simply say 0 for every single row. And in terms of accuracy, or in the eyes of accuracy, it aced. So technically, your model did not learn anything, but still, accuracy is going to tell you that, hey, your model was accurate. That's because it's highly misleading. Precision tells you that if my model were to make a prediction, how accurate will that be? For example, if a model has been trained and if the precision of model is very high, and whenever it say like the final output is 1, which let's say survived, and since its pretty precision is high, when you're going to cross check that testing data point with the y test, you're going to realize it's going to be 1. So precision is like basically when your model is 100% sure, only then it will see the output. And recall is basically that out of true positives, how many true positives I got. So recall will not care a lot about your accuracy. Recall, in recall, basically, even if it won't mind saying something which is 0 1, but it's going to make sure that all the true positives are being caught. F1 score is nothing but just a simple harmonic mean of recall and precision, trying to just balance out both of them. um okay, so let's move on to the
Shirish,
huh
to jump
am
in
I
here, the error that we were getting was because of a syntax error. We can replace that with underscore predict prob. So predict underscore proba. That is the correct syntax that needs to be followed. And for the viewers' benefit, of course.
predict underscore proba? Okay. This. Yep.
Underscore instead of p x text scale, just do x scale. The pt is not required. Just use x underscore test underscore scale. The p and underscore in front of that is extra. That is probably because it got misplaced.
Or maybe a typo from my side. Yep,
Yeah,
yep,
yeah,
yep.
yeah.
Okay. Okay, thank you so much.
Yep.
Uh, okay, so let's move on to the ROC curve. Okay, so what basically ROC curve tells us is that it's a plot of all the false positive rate and the true positive rate. So this red line is if you have been the line, and this blue is basically the performance of your model. Technically speaking, a good ROC should be always on the very top left, and AUC stands for area under the curve, which is telling us that it's 85%. And we use basically ROC curve to decide the threshold values. Moreover, we use PR AUC, which I haven't covered over here because we aren't actually focusing on the threshold optimization. But uh, you use this basically to see for all the different range of values. Okay. Also, there's one more thing which I commented off because of that variable error I had. It was log loss. Basically, what log loss does is, okay, it tells you for example, and the more higher the log losses, the more worst it is. Your model, since it should be predicting correct things with a high confidence level, that confidence level judgment uh, is quantified by log loss, and your entire model is always trained on log loss. Okay, so this was just one example over here. We can now move to the next example where I'm going to quickly show you decision tree example. Now, personally, decision tree would be one of my favorite model, and that's mainly because, as you see over here, we have to do a lot of things. We have to scale that entire dataset values, and we have to make sure that there are no outliers inside of it, etc., etc. So the pre-processing part is quite huge over here. Uh, but decision tree functions on completely different way. It does not work on the concept of gradient descent itself. So that's why decision tree is, in my is one of my favorite model, because you do not have to work a lot or tamper a lot with data set. In fact, if you were to even encode in logistic regression, let's say, certain values would have been ordinarily encoded and other would have been used by one hot. But over here, we can just directly encode all the values into integers, and it will not affect the performance at all. So again, let's just quickly import all the values. Oh, sorry, all the libraries. This time I'm going to use a different data set with the name of tips. It's again directly you can get that thing from Seaborn. Okay, it's the same part, just quickly checking off the data set and checking if it has a null value or not, which we can see over here it does not. Okay, now over here I'm basically making a new column where I'm just trying to classify if the also to data set, this data set basically represents that how much tip was given to let's say a waiter, and on what day, etc., etc., and these are the other features for it. Okay, so again, this is the same part, just splitting off and deciding what is our target column and what is our target row. Yeah, in this we are basically converting all the see, basically over here we have categories, right? We're converting all of that into numbers over here. So that's the part of this line where I'm iterating uh, the dataset columns. I'm using dot select data type, include object and category. Basically, I'm selecting a certain type of data from this bigger data set, which only includes or whose data type is object on category. Dot codes basically encodes them into new integers. Okay, right. After this, again, the same part splitting of data set, which I have already give you a quick walkthrough. Okay, now let's move to training of the model. In this, I have again used max underscore depth equal to 3. What this parameter primarily does is, uh, it makes sure basically it tells the model that you can only go till the level of 3, as explained by Arav, that there's a main node and then there are small splittings which are happening till the time you obtain a leaf node. But in this, since I've capped the maximum depth as 3, no split is going to happen beyond 3. Criteria, there are two criteria, entropy and Gini. Entropy is something which is covered again by Arav, and Gini is a criteria which is again like beyond this course. But just consider for the time being this, that if the data set is too big, you should use Gini because it's far more quicker, but entropy is far more accurate. Okay, let's quickly train our model. And this is one way to like display your entire model, the entire tree over here. What I've basically created an instantiate the entire model under the variable of tree. This 1, 2, and 3 because the max depth is 3. And moreover, in this we can see the entropy of this is 1. It's already a pure node. Similarly over here it's 0. So if I were to increase the max depth, these two won't increase, but this will again increase, because over here the entropy is not a complete entropy, like it's not either 1 or 0. Okay, so that covers the decision tree part. Now let's move on to ANN, artificial neural networks. So this is a part of DL. These two are a part of ML. Let's again quickly import all the necessary modules for this. Okay, 1 second. It's taking a lot of time. Okay, I think I should just quickly restart the runtime once. Okay. Okay, yeah. Okay, it surprisingly took a lot of time. Let's quickly load the data set. So in this, I've used a data set with the name of breast cancer. And again, in this, I'm just defining that this is the target and these are the individual independent features. Okay, now I'm going to split the data set early, again, in order to avoid any sort of data leakage. And let's quickly have a view of the data set. Since this actually is a real medical data set, so it has a lot of features inside of this. Okay, and over here, since ANN, again, they use descent to update their weights, we have to again use scaling over here. And since we're using scaling, again, the good practice of using .fit underscore transform and train, and in test, just using transform. Okay, now here the fun part begins. So over here, basically what I'm doing is I'm trying to describe the entire architecture of the model. So dense is basically me allotting layers of neuron. And we have three things. We have the input layer, we have the hidden layer, and then we have the output layer. Batch normalization is something which I have to do after I introduce a layer. And Okay, if I were to go completely in depth, it's a concept of geometry which is used in deep learning. But if I were to quickly summarize it, it's basically like, since we are moving from one layer to another. Okay, so okay, let's just quickly visualize it. We have first layer as the input layer, you have hidden layer, and then you have the output layer. Now each layer, they're updating of the weights, right? So we know that z equal to wx plus b, so now it basically updated to the certain value of w and b. And now when the information is passed from one layer to another, so the second layer, it will receive the information from the first layer itself. And since it's not the original information, if we do not use normalization, the data is going to be quite messy. So what normalization does is, it basically uh, introduces certain range limits, like mean equal to 0 and variance equal to 1, so that the next layer actually knows where to start from. For example, if I were to hand over you a note, let's say notes of a certain subject, but I did not taught you the prerequisite of that subject. So that's the same case which is happening over here. If I did not use normalization, and if I were to directly move from one layer to another, the next layer has to figure out what the previous layer figured out, and then it will do its own contribution. And just to avoid all this, because it's just increasing the workload and it's going to impact the performance, we use normalization. Okay, then we move on to dropout. Dropout, basically what it tells us, it drops the neuron in between randomly. Point 0.3 is the percentage that 30% of the neurons are going to be randomly dropped in between. Now the question is, why are we doing that? Because more neuron means more training, like more raw power. And this means that it should boost our model's performance. The primary reason why we are doing this is because if we do not do this, let's say, the model might find in itself a path, and it might use that same path every single time. So we are forcing the model to think of something new. And because of that, we are introducing chaos inside the layer by randomly killing certain neurons, so that the model has to learn something on the spot. It has to learn something new, and then it might go to the final answer or to the final output. So basically, yeah, the model can't rely on just one singular path, and it has to learn new patterns. Now notice how we are decreasing the size of the neurons from like 64 to 32, 16, and then 1. This one is finally the output. So it's just the entire architecture that the input layers are huge, and then we move on, and we uniformly like decrease all the layer till the time we go to the final output layer, which will always have one neuron. Okay, now Activision function, as covered by Arav, basically it tells that which all neurons would be activated in the next layer. We have optimizer function, loss function, and activation function. So activation function primarily decides which neuron should pass the relevant information from one layer to another and which should not. And ReLU it's again one of the most famous activation function. Again, I don't want to go more depth into ReLU. Again, that will take things a bit more advanced. So we'll keep this on hold and probably cover this some other lecture. Let's quickly run this. Now, this was defining the entire architecture of the model. Now, over here, I'm just saying that, hey, I've created the model. Now, let's create it IRL. Like, let's just compile everything, just like how the compiler works of your any language, like let's say C. Same thing over here. Okay, so optimizer is Adam. In my eyes, I'd say Adam is one of the most goated optimizer. And since in this course you have learned gradient descent, Adam optimizer, what it basically does is gradient descent, it descends uniformly, right? Adam optimizer is smart enough that it descends in uneven steps. It basically initially descends at very high or with large amount of steps, and then later on it decays it and goes into a smaller amount of steps, so that the training is basically more fast and more efficient. Moreover, it also suppresses the zigzagness which the gradient descent might have. But again, it's the most best optimizer. It handles both the IMS prop and the momentum. Okay, Now let's move on to loss, which I have used binary cross entropy. Basically, again, not going completely into depth, but if your output is of just two classes, ones and zeros, like for us it is whether the person has cancer or not, we use binary underscore cross entropy for that. And let's say if there were multiple classes, then we use softmax, and so on. For different cases, we use different loss functions. Matrix accuracy is just the matrix which is going to be followed while the entire compilation is done. Okay, now this is where the entire training happens. Epochs is the iteration, like the entire front propagation and back propagation. That's one. Batch size 16, because we're going to not just do that for every single row. It's too inefficient. We're going to send a batch of 16 16s. Validation split is basically like we have k-fold CV in machine learning, something like that. What it does is it takes 0.1, that means 10%. It's taking 10% of that certain batch, and rest all is again used for training, and that 10% it's used for the evaluation through which we're going to use, which we're going to see over here, these values. Okay, so yeah, let's quickly jump into the training part. Oh yeah, and verbose equal to one. I forgot to explain this. Verbose equal to one is just this interface you see. Like if you have equal to 0, it's not going to show anything. If it's 1, you get to see the accuracy loss and val underscore loss, etc. If it's 2, it's more detailed than this. So we're done with the training. Again, the same thing. We have y prediction, which gives a prediction, and then y pred proba, which is the intermediate probability, basically. Okay, and at the end, summing everything up, we have accuracy, and again, basically the evaluation, which tells us that we have 97% accuracy, and the ROC curve, which is right over here. And as you can see, it's 99, which is quite huge, and it's on the top left, like it should be for the ideal model. So yeah, that pretty much winds up the coding aspect of this session as well. I hope it was fun, and let's just quickly go ahead. You guys can scan the QR for the attendance, and in the meantime, Ashutosh can cover about the DevSOC website.
So, guys, DevSOC is the largest hackathon in VIT in Yatra. And Shirish, if you can just show the landing page.
Just one second. I actually, okay, you know what? I'll first show the website, then you can scan the attendance. Yep.
Guys, so DevSOC is happening from 8th to 11th. And this is one of the largest hackathons in Yantra. Registrations
South
are
Asia is one of the largest South Asia's hackathon.
Right.
Yep. So do register, guys.
Registrations are live on VTop and they are free. And there's a very good prize pool as well. So there's a lot for you in DevSOC. So looking forward to meet all the viewers in DevSOC.
And these are our guest speakers, which would be invited. We have Google techies and a CTO of Hotfoot. Okay, so let's just go back to the attendance.
You guys don't want to miss it, so please register for DevSOC.
On VTop under SW events, guys.
Oh yeah, and if you guys have any questions regarding today's session, we are open to answer them.
also, guys, if you have any more questions about DevSoc, you can contact us on our Instagram page or anybody from the EXE course group or any CodeChef member that you know.
Sexy classic.
Guys, we have speakers coming from Google, so you don't want to miss that. So you should register for DevSoc.
I'm considering classic only sorry. I'm considering classic only sorry. There's no case. TP out. TP out. TP out. TP out. Yep.
DevSoc is super beginner friendly. So even if you guys are starting for the first time or you just want to learn, you should come off. And it's a great environment, and we have really good speakers coming, so you don't want to miss. So we will see you at DevSoc. And if you have any doubts regarding this session, you could come meet us in DevSoc for getting them cleared personally. Yeah.
Aditya asks, what is transformers? I think where transformers he is commented, but I think he means what are transformers in ML.
I
So
can send market.
if anybody wants to take, or I can take it.
Oh, I'm sorry, could you repeat the question?
I think he's meaning to ask what are transformers. It is something that we did not cover, but in brief, Aditya, transformers are basically machine learning architectures that work on an algorithm called self-attention algorithm. So over here, you take all the inputs together at once. The model is looking at all the inputs together at once, and it's a highly efficient way to deal with sequential data. Although, oh, why we didn't cover transformers? Aditya, there's only so much we can cover in a given span of time, right? So
Transformers are basically the king of NLPs. Not just that, but anything which has sequential data, yep, just blatantly transformer. Nobody even use RN and LSTM right now.
yeah. If you guys really want, we can keep a session on transformers and advanced machine learning concepts in the future.